Shear force and bending moment diagrams. Let's look at some of the learning outcomes. Understand the shear force diagram and bending moment diagram, and be able to construct shear force diagrams and bending moment diagrams using the procedure. Consider a beam with the distributed loading W of x, where we define W of x as positive downwards. Consider an element that's delta x long. Assume W of x is constant over the length delta x. All internal forces and moments are shown as positive, and delta v and delta m are required to keep the element in equilibrium. If we take the summation of forces in the y direction and then take the limit as delta x approaches 0, we get the following equation where dv over dx is equal to negative w of x. This is our first equation. If we take the moment and then take the limit as delta x approaches 0, we get the equation dm over dx equals v, which is our second equation. Let's consider shear force and bending moment diagrams for the beam, where we rewrite equations 1 and 2 as dv is equal to negative w of x dx and dm is equal to v dx. We integrate these expressions between points 1 and 2 along the beam length. This gives us our third equation, where change in shear force between points is equal to the negative area under distributed load diagram between the points, and our fourth equation, where the change in bending moment between points is equal to the area under the shear force diagram between points. Let's look at the procedure for the shear force diagram and bending moment diagram. First, we'll draw the free body diagram of the beam and compute all support reactions. Resolve all forces acting on the beam into components parallel and perpendicular to the beam axis. Let's take a look at this beam where there are support reactions AY and DY, a concentrated load P, and a distributed load W. For shear force diagrams, they are constructed using the support reactions and loading diagram for the beam. We start at the left of the beam and follow the load across the beam. Concentrated loads and support reaction forces push the shear force diagram up or down depending on their sense. The shear force diagram is constant between concentrated forces and reactions where no other loads are applied. Distributed forces gradually push the shear force diagram up or down depending on their sense. Let's create a shear force diagram using the beam in the previous slide. First, AY will push the diagram up by an amount AY. This is constant from point A to point B. The concentrated load P will decrease the diagram by an amount P, which is constant from point B to point C. The distributed load will decrease the diagram linearly by an amount W from point C to point D. dy will push the diagram back to equilibrium, which is at 0. Let's continue with the shear force diagram. The change in shear force between 2 points is equal to the negative area under the load diagram. A downwards load produces a negative change in the shear force diagram. The shape of the shear force diagram between 2 points depends on the load function. The slope at a particular point is equal to the negative magnitude of the load function. And equation 3 allows the shear force magnitude to be computed at various points along the beam. Now let's look at bending moment diagrams. The bending moment diagram is constructed using the shear force diagram, and we start at the left end of the beam and graphically integrate the shear force diagram. The change in bending moment between 2 points is equal to the area under the shear force diagram between the points, and a positive area under the shear force diagram produces a positive change in the bending moment diagram. The shape of the bending moment diagram between 2 points depends on the shape of the shear force load function. The slope at a particular point is equal to the magnitude of the shear force diagram. Let's create the bending moment diagram using the shear force diagram from the previous example. We start with A1, which is constant and positive. This gives us a linear function that has a slope of AY and ends at A1. Same thing with A2. It is constant and positive, therefore linear, and will end at A2. It will have a slope of AY minus P. A3 is above zero and positive, meaning the bending moment diagram will increase parabolically. We will have the maximum here due to the zero. A4 is under the zero, which means our bending moment diagram will decrease parabolically and then go back to zero through dy. Let's continue with bending moment diagrams. Concentrated moments and fixed support moments will push the bending moment diagram up or down depending on their sense. Equation 4 allows the bending moment magnitude to be computed at various points along the beam. The location of the maximum or minimum moment corresponds to the location where the shear force diagram is zero. Concentrated forces and moments. A downwards force P causes the shear force diagram to jump upwards by an amount P. An upwards force P will cause the shear force diagram to jump upwards by an amount P. A clockwise couple C will cause the bending moment diagram to jump upwards by an amount C. A counterclockwise couple C will cause the bending moment diagram to jump downwards by an amount C. Based on the first two equations, the following relationship is observed. If we have a concentrated load, the shear force diagram is constant and the bending moment diagram is linear. A uniform distributed load will give us a linear shear force diagram and a parabolic bending moment diagram. A linear varying load will give us a parabolic shear force diagram and a cubic bending moment diagram. In general, if we have a load that's degree n, the shear force diagram will be degree n plus 1, and the bending moment diagram is n plus 2. Local maximums of moments will occur at locations where the magnitude of the shear force is zero. The bending moment diagram will often be parabolic or higher order functions. Make sure the shear force diagram and the bending moment diagram are consistent with support conditions and hinge locations. Moment should be zero at hinges. The moment should be zero at the ends of the beam unless there is a fixed support or concentrated moment applied. Shear force should be zero at a free end unless there is a concentrated load. To summarize, shear and moment diagrams are graphical representations of the internal shear and moment within a beam. Shear force diagrams are constructed using the load functions, and bending moment diagrams are constructed using the shear force function. Proper sign convention must be used.